Let us prove the chain rule. So let's write out our setup. Let's let x, y be domains in the real numbers. F is a function from x to y. And G is a function whose domain is y and whose range is, say, the real numbers. Let's let A be a point in x, and we're going to suppose F is differentiable at A. And also that G is differentiable at the point f of A. Then the function G composed with F is differentiable at A. And we've got the formula that you no doubt remember. We've got the chain rule formula that we all know and love. G composed with F prime of A. That's G prime of F of A multiplied by F prime of A. So let's go ahead and prove this. And to prove this, we're going to use a gadget that's going to come in very handy in chapter 6 when we're trying to do multivariable calculus. So let's define the following function. We're going to let capital F of x, that is going to be the following piecewise defined function. It is going to be this difference quotient, f of x minus f of a over x minus a. That's true if x is in the domain of x, except, don't divide by 0. And we're going to say that capital F of x, actually we're going to subtract f prime of a here, and then we're going to put a 0 down here if x is equal to a. And then by proposition 2.1.5a, we have that the limit as x approaches a, capital F of x equals 0. So big F is continuous at A. And then furthermore, if x is anywhere in our domain, either equal to A or not, then we can write that f of x minus f of A, that's equal to x minus a times f prime of a plus big F of x. If x is equal to a, both sides are 0. If not, you just do a little bit of algebra on the first case. And then similarly, we're going to let the function g of y, remember, g has domain big Y, we'll call that will be g of y minus g of, and then we drop in our f of a over 1 minus f of a. Then we subtract off g prime of f of a. if y is in the domain of g minus f of a, and it's going to be 0 if y is equal to f of a. And then, so the domain of g is the same, of big G is the same as the domain of little g, and g is continuous at the point f of a. Now here's what we're going to observe. Little f is continuous at a. That's true by proposition 2.2.4, that differentiable functions are continuous. Big G is continuous at f of a. So here's the thing to notice. Big G composed with f is continuous at a, and that goes all the way back to section 1.7. This is proposition 1.7.4 on composition of continuous functions. We don't actually have a lot of good propositions on composition of limits. They'd be tricky and finicky, but we do have a composition of continuous functions. So let's write the limit as x approaches a, g of f of x is g of f of a, because g composed with f is continuous, is 0. And that is by corollary 2.1.3, that if you're continuous, then your limit is equal to your value. And then we're going to need the following fact. It's pretty similar to the thing we proved for big F before. If y is in the domain of g, then g of y minus g of f of a, that's going to be equal to y minus f of a times g prime of f of a plus big G of y, and in particular g of f of x minus g of f of a, that's equal to f of x minus f of a, and then we've got a g prime of f of a and a big G of f of not a but x. Now let's put this all together. So g prime of f of a times f prime of a. We're going to write that as g prime of f of a, limit as x approaches a, f of x minus f of a all over x minus a. And then I'm going to go ahead and add 0 to this. G prime of f of a, limit is x approaches a, f of x minus f of a all over x minus a. And then I get to add the limit as x approaches a, big G of f of x. We saw before that this limit is 0, and then I get to multiply that by anything I feel like, as long as it's finite and exists, and as it happens, I'm going to go ahead and multiply by f prime of x. And we notice all those limits exist. So our usual, our favorite proposition about sums and products of limits, we're going to go ahead, write this again, g prime of f of a, f prime of a, that is equal to the limit as x approaches a of great big brackets f of x minus f of a, and then a g prime of f of a, and then we add that to that another f of, and then we can go ahead and factor out the f of x minus f of a and just put in a big G of f of x. Then the whole mess gets divided by x minus a. And then we recognize from back here that f of x minus f of a times g prime of f of a plus g big G of f of x, that is just equal to g of f of x minus g of f of a. Or it can write that using composition notation. G composed f of x minus g composed f of a. So, and that we've got written there is exactly, that difference quotient is the difference quotient of the definition of G composed with F prime. So G composed with F prime of A exists because this is a limit, because all our limits exists, and equals G prime of F of A, F prime of A. And that completes the proof of the chain rule. And this trick where you write G of X as G, where you write f of x as f of a plus f prime of a times your linear factor x minus a, and then your linear factor again times some small error term that will come up later. And I admit we only used capital G. We didn't actually use capital F, but I thought it would be a lot easier to explain what was going on with capital F so that I wouldn't have to be writing f of a all the time. Now I am going to define local extremum. I'll write down the definition of a local maximum, and I'll leave it to you to deduce the definition of a local minimum. Let's suppose we've got some domain, some function on that domain, and some point in the domain. And let's suppose that the following statement is true. Suppose there exists a number a positive number delta such that for all x in x with the distance from x to c less than delta, we have that f of c is bigger than or equal to f of x. We want to include the equals case because, after all, c is a number in our domain whose distance to c is less than delta, because the distance from c to itself is in fact 0. Then we say that f has a local maximum at C. And here is a theorem. I'm going to mention here that most of the results in section 2.3 you really need to be working with functions defined on intervals, and in a lot of cases on functions defined on open intervals. So let's let f be a function whose domain is an open interval, and we'll go ahead and say that the endpoints are allowed to be plus or minus infinity, but we are going to insist that this has to be an open interval, not a closed interval. And let's suppose let's suppose that C is a point in our interval. F is differentiable at C. And F has a local maximum or local minimum, but I'm going to state it for maximum. Prove it for maximum, that is. And then the conclusion is that we know what f prime of C is, and it's 0. Quick sketch of some of the ways this can be strange. For example, this function has a local maximum right here, but the derivative doesn't exist, so the derivative is not 0. Other example, and here's why I made such a fuss about the domain. It has to be open. This function has a local maximum here at its endpoint, but the derivative there certainly isn't 0. So when we prove this, we'll be proving this for an interior maximum where the derivative does exist. So let's let delta be as in the definition of local maximum. And then if x is on the C minus delta side, so on the negative side, then our difference quotient f of x minus f of C over x minus c. F of x is less than f of c, so the numerator is negative. X is less than c, so the denominator is negative. So this is certainly positive. Then similarly, if x is on the other side, then our difference quotient the numerator is still negative, but now the denominator is positive, so we've got 0. Now, let's suppose f prime of c exists, and f prime of c is not equal to 0. So this is going to be a proof by contradiction. So let's let epsilon be the modulus of f prime of c, the absolute value. And f prime of c exists. And remember, this is f of the limit as x approaches c, f of x minus f of c all over x minus c. So that limit has to exist. So this thing necessarily, so let's let delta, well, we've already used delta for something. Let's let eta be such that if 0 is less than x minus c is less than eta, then we've got f of x minus f of c over x minus c minus f prime of c is less than epsilon. But you remember what we said epsilon was. It was absolute value of f prime of c. And then, so by the reverse triangle inequality, so let's say if f prime of c is positive, then pretty simple argument with the reverse triangle inequality, this difference quotient, that also has to be positive if x minus c is less than eta, and also if it's positive and less than eta, that is. And but there is at least one x that's in our interval with, let's see, we want c to be less than x to be less than c plus whichever is smaller, delta or eta. So we must have that this difference quotient, it's got to be positive if the distance from x to c is less than eta, which it is, but it's also got to be negative or 0 if the distance, if x is between c and c plus delta, which it is. And this, of course, is a contradiction. That can't happen. So we see that f prime can't be positive. Then similar argument. If f prime of c is negative, then, and we've got f of x minus f of c over x minus c, that also has to be negative. It's less, but this difference quotient has to be positive for some x with c minus whichever is smaller, delta or eta, less than x less than c, and that's also a contradiction. So if f has a local max, at c, and f prime of c exists, then we must have that f prime of c is equal to 0. And then if f has a local minimum at c, then minus f, that's the function, and where you would take f of x and multiply by minus 1, that has a local maximum c, so minus f prime of c equals 0. So then just multiplying by minus 1, f prime of c is minus 0, better known as 0. And so that completes the proof in both the maximum and minimum case. And then there's the classic example. So let's let f of x equal x cubed. Then f prime of 0 equals 0, but f does not have a local minimum or maximum. The term for that is extremum at 0. So this isn't an if and only if statement. There are plenty of functions where the derivative is 0, but you just have a point where you're flat. You don't have a local minimum or a local maximum. Next thing we're going to do is we're going to prove the mean value theorem. You might have seen this in freshman calculus and not been quite sure what it was all about, and that's because what it's all about is that the mean value theorem is what lets you prove a lot of the cool results in calculus. So it's a theorem that gives you a bunch of other theorems. It's not something you immediately use itself. So here's how this works. Let's let f be a function whose domain is this closed interval from a to b. This is a closed bounded interval. A and b are both real numbers with a less than b. And then we're going to suppose f is continuous on this closed interval. That means right continuous at the left endpoint, left continuous at the right endpoint. If f happens to be defined outside AB, we don't care what it's doing out there. We just want f to be continuous at every point in this closed interval when you only look at points in the closed interval. And we also want f to be differentiable at every point in the open interval from A to B. So we don't insist that f has to be differentiable at A or B, but we do need it to be differentiable everywhere in between. And we really need everywhere in between. The mean value theorem is very much a theorem about intervals. If you've got missing points, this doesn't work. And the conclusion is that then there is at least one point in our open interval such that we can write this equation. F prime of x is this difference f of b minus f of a whole thing over b minus a. Let's prove this. So we're going to let the function h of x, we're going to write f of x minus f of a minus, and then we're going to take, let's say, x minus a, and then we'll put an f of b minus f of a, and then a b minus a. So this is a new function, but it's a lot like our old function. Remember, f of x by assumption is continuous, then f of a is a constant, our difference quotient f of b minus f of a over b minus a, it's complicated, but it's a constant, and then x minus a, it's not a constant, but it's a linear function, it's a polynomial function, it's a very nice function. So h is continuous on the same place where f is continuous, because everything else is just polynomials, is just nice stuff. And by the same token, h is differentiable on this interval from A to B. Okay, so by continuity, so by the extreme value theorem, so remember, AB is closed and bounded. And H is continuous on AB. And that's what we need to be allowed to apply the extreme value theorem. This, remember, is the one that says a continuous function on a closed bounded set attains its maximum and minimum. So there are points x, y in our interval such that h of x is the minimum and h of y is the maximum. So h of z is between h of x and h of y, and that's true for all points z in our closed bounded interval AB. All right. What is h of a? H of a, if you plug through it, f of a minus f of a, and then an a minus a is a 0. H of b, f of b minus f of a minus b minus a over b minus a times f of b minus f of a. H of b is also 0. Simple arithmetic, simple algebra, everybody in this class can do it. So we have of that h of x is our minimum, is less than or equal to 0. You take z to be a or b. It's less than or equal to h of y. So two options. If h of x is equal to 0 and so is h of y, then we have that h of z equals 0 for all z in AB. So h prime of z, the derivative of 0 we all know is 0, so I can just put a 0 here, but then we write it out, we get f prime of z, and then the f of a goes away, the derivative of x minus a is 1. And then if we were to apply the product rule, we'd get x minus a times the derivative of that difference quotient, f of b minus f of a over b minus a, which I know looks complicated, but is just a constant. So its derivative is 0. So we get that f prime of z equals f of b minus f of a over b minus a for... In this case, it's not just sum, it is for all z in this interval from a to b. So now let's look at the next case. If h of x is less than 0, then, well, the first thing is that x cannot be either of our endpoints. It can't be the left endpoint A. It can't be the right endpoint B, because h of A and h of B are both 0. So x is in AB and is a local minimum. So h prime of x equals 0 by theorem 2.3.2. So just as before, f prime of x, that is f of b minus f of a over b minus a. And in this case, we've only got 1 point with the right derivative, but that's okay. That's all the theorem asked for, was 1 point. And then similarly, I don't feel like writing it all out. If h of y is greater than 0, then y is still not an end point because h of y is not 0, and same argument as before, f prime of y is our difference quotient. Let's draw a nice picture of the mean value theorem. Here's A, here's B, here's our function. And then the mean value theorem says if you take the line through a f of a and b e f of b e, then there is some, you can find some point into where the derivative is the same, where the slope of the tangent line, better known as the derivative, is the same as the slope of the secant line. In this case, that point would be right about here. There's your x. In this case, it's the local maximum. If I draw this picture oriented the other way, with the graph oriented the other way, it would be a local max. It would be coming from the local maximum of h. Sorry, this is coming from the local maximum of h. If I'd drawn the graph going the other way, it would become, your point x would be coming from a local minimum of h. And then if you've got a point where the derivative doesn't exist, the mean value theorem doesn't work. And if your domain is not an interval, then your mean value theorem, then you might have a gap like this in your domain where your function can jump up, and then your mean value theorem again won't work. Now let's see a couple of applications of the mean value theorem to prove some fairly common results. Let's let f be a function defined on an open interval. Not going to write out all the conditions of open interval again. And let's suppose f prime of x equals 0 for all points x in our interval. And when I write that, I mean f is differentiable and the derivative has the value we wrote down. And the result is that f is constant. And proof is pretty quick. Let's pick a point C in this interval, and let's let D be any other point in this interval. And then you apply the mean value theorem on the closed interval from C to D or D to C, depending on which of them is bigger. Our function f is differentiable everywhere between C and D, and differentiable implies continuous, so it's continuous on C to D. Then, and for some x in CD or DC, I don't care which one, x is in AB, we have that x is in AB, so it can go ahead and write 0 equals f prime of x is f of D minus f of C over D minus C. So f of D equals f of C. So any point in this interval has the same u is f of c. Any 2 points have the same value, so f is a constant, f of d equals f of c.